What was the homework? Oh, have you guys finished the homework?
Yeah, most things
How is the homework going?
is very tight. But it's
What
okay.
does that mean?
I mean, like it's lots of problem. That's why it's taking a long time, but we get.
But is
Yeah.
it working? Whatever you finished, is it going good?
Yeah.
Does it make sense?
Yeah.
Does it make sense? Like you're.
Yeah.
After trying at least.
Yeah, we get like from start to last, we get like a clear idea about this functioning derivatives.
Who's up? Okay. Okay. Homework 3, I'll post it in a few hours, hopefully. It's just a matter of how much I want to change the whole homework. That's all. What's the mumbling?
I just see the February 30.
Yes, February. Isn't that right? 6 plus 7, 7.
Yeah.
It's not clear. Midterm 1 is in 2 weeks, I suppose. 2 weeks plus 2 days. Yeah. So when you're doing functional derivative, I think there was a comment made by one of you guys, whether you have to do it or prove the fact that this really works. You don't have to, as far as you get the result right. I'm fine with the homework, but in the exam, there will be one question, which will be a straightforward one, where I'll ask you to do it ab initio method. That's what it is called. Like you, if I were to ask you to prove that derivative of x cube is 2x squared, you cannot just write 2x squared. You show that, make the limit or change the function at x, subtract it, and then divide by delta x. And so that it's called the ab initio method. In my understanding, that's what Newton, that's how Newton used to do it. And so you have to do the same thing for the functional derivative also. Simple ones, it won't be elaborate functions like x. When you do a ab initio method, you try to do simple ones like x cube or x raised to 4. So that's all. So in the exam, at least one question you can be, or two questions you can be sure about. One will be a functional derivative with ab initio method. Second one will be a functional derivative itself, like which will be more involved. And then as we proceed to see more questions. So okay. Now that presumably you have an idea of functional derivatives, we can do problems that is associated with the calculus of variations, mostly minimizing some quantity. Earlier in Fermat's theorem, it is a time that is minimized. You don't have to minimize time, you can minimize distance, or for that matter, any quantity. For example, action is a quantity we'll be interested in. We can minimize that. So before we proceed, so it is good to, I think, so again, functional derivatives sort of summary. Usually, you have a quantity, maybe time or anything. It depends on a function. Let's say, I think we have been calling it u. Right? It's a function u of x, for example. So this should be understood as it's a function of. So it's a functional, right? So the square brackets means it's a functional. That means it could be any function. You think of any arbitrary function here. and you integrate this. And the quantity that is inside the integral, let's call that I, in general, is a function of u, right? U there, and now that I'm writing explicit form, it is inside an integral, I can explicitly write x. Here I cannot write x, and why cannot I write x right there? What's wrong in writing t of u of x? Right, here I do write x, let's say.
In function, we cannot write yes.
Yeah, why not? That's a question.
Square brackets.
Square brackets.
Yeah, that's a-
Function.
Yeah, that's a prescription, but what if I write x? What is wrong in that? Right?
Then u of x is. Function.
Is that question clear? Maybe if I write this, it's better.
That's the limit.
Like, my question, I think, is if I write integral of x, d of x, f of x, right? That's an integral. And I say x1 to x2, what does this depend on? Let us even say, yeah, x1 and x2, right? Let's even say sine of x, for example. Right? If I specify that this never depends on x, correct? It only depends on whatever this quantity is. It only depends on x1 and x2. It only depends on the limits. So here, if I write x, that means that it depends on x, but it doesn't depend on x. It only depends on the boundary points. It depends on the functional form of u. If I do sine of x, this is different. If I do cosine of x, it's different. Tangent of x it depends on the function, but not on x. It depends only on the boundary of x. So more strictly, you can say this is u, and sometimes you also say it depends on x1, x2. But we don't change the boundaries, right? We are keeping the boundary fixed. So we don't even write x1 and x2. In general, it can depend on x1 and x2. We will come back and address that later on. So that's the reason why I don't write x there. But here, what are the quantities? It can depend in general on the problems that you have worked on. It depends on u of x, then it can depend on the derivative of u. So this should be thought of as an operator acting on u. And in general, even higher derivatives, right? You can write second derivative of u and so on. But let's consider the situation where it depends only on this, and it could depend on x also. Very quickly, you want to depend, like we will change our whole analysis and say this is the path or the trajectory of a particle. X will become time. If x is time and it is derivative with time, it is a velocity. So it depends on the position, trajectory, the velocity on the trajectory, and the time itself. That will be our goal. So that's what Lagrangian and Hamiltonian will be about. But here at this point, we are just practicing how to do functional derivative. So we have any arbitrary function of u, where u is a variable, like u is the function that is changing. And in general, this can depend on that. If I want to do the functional derivative with respect to u, this time of, let's say, x prime, how will I proceed to do this? Remember how we were doing this. You pretend as if you're taking the derivative with u. And at the end, you bring in the delta function if you want, or the variation of u with respect to x at x prime, right? So I can enter this. So this is x1, x2 dx. And now I have to take the derivative of this with respect to u. There are two places where this u shows up. So I will take the derivative of those two quantities. First one, this, since I don't specify it, it's the derivative of I with respect to u. I pretend as if I'm taking the derivative with respect to u, and then At the end, I put u x with respect to u x prime, correct? If you want, this is x. Correct? Is that clear what I'm saying? Yeah, you right. The functional derivative of delta t. Oh, yeah, you. I think somewhere I thought I read. Yeah, mixing up. Thank you. Good. So when I'm taking the derivative with respect to a change in the function, our manipulation is that pretend that this is a variable u, take the derivative, that's your derivative, and at the end, argument of u is taken the derivative of, then you say this is a delta function. You have to do the same thing here, so it is plus. This time, you take the derivative with u, right? It's like taking the, if I say it's a velocity, it's a derivative of u itself. So how will I do that? Wherever I see the derivative, I have to do that. So I have to explicitly write that. Is that clear? So that's whole thing, you treat it as a single quantity. And the derivative of that itself, so this is d by dx of delta u of x. And x doesn't change, right? So if this makes sense, maybe I should give you an example so that you see how this isn't working out. So example, right? So I'll erase this, but just to give you a feel for this. It's too abstract maybe. So t of u could be x1 to x2, t of x. And let's say it is, this I is nothing but square root. So let's say it's square root of u of x times a of x plus d of x times du by dx. That could be a simple example. And how do I do this? Equal to, first I look for u's, so that is a u here and a u here, but I'm treating this u either as a u or a derivative of u. So first look for derivatives. Sorry, first look for u itself. Right, so this is 1 over, so that's 1 by 2 times 1 by 2 minus 1, it goes down, right? So this is square root u times a plus b times du by dx. I shortened this, so understood that the x dependence is in there. And take the derivative of u. So this is basically the derivative with respect to u, but there is a there, that argument. And finally, du by dx. Say variation of u at x with respect to x prime. That's the first term. When I do the second term, this time I'm thinking I'm taking the derivative with the du by dx. So again, I do 1 by 2 square root of u times a plus b times du by dx. And this time, look for derivative of u. So that's d of x found in this d by. Right? It's such clear. This whole thing is derivative of the quantity with respect to u. Derivative of the square root with respect to u. This whole quantity is the derivative of the quantity with respect to derivative or u prime if you want, right? So if I were to use the notation u prime is du by dx, this quantity is, if this was I, this is di by du. Simple derivative. This is di by du prime. So whatever be the function, take a simple derivative with u, and take a simple derivative with u prime. With u associate this term, and with the derivative of u prime associate, because that's the argument, right? Eventually the argument when you take the derivative, that's what you get. Is that clear? Okay. So that's an example. So we go back and here. So that's an illustration of how that works. If that's the case, I can do integration by parts. I think I think Manuka pointed out that in the homework question, I mentioned differentiation by parts. I think it is more commonly said, I think it is called integration by parts. I use the language differentiation by parts. What is differentiation by parts? Is that no? There is no such thing as differentiation by parts, I suppose.
No, integration, but.
Yeah, it is integration by parts. Well, that's my error, so hopefully didn't confuse you guys. Oh, if I do integration by parts, I can make this derivative act on this instead of here, and that is a surface term. So this is equal to x1, x2, x I u. Because the main idea is that this is not common, right? These two are not common. I want this to factor out. So it is minus let's remember that this u prime means that, okay, so I try to avoid those notations, but this is this. Let me also close the bracket here. That means this derivative doesn't go beyond this curly brackets, and then I have. That's not completely correct because I moved the derivative, so I have to compensate for that. So that's the compensation. So that's agreed. I think of this as this is how it should be. If when I act on this, it can act on this or that. When I also the second term, that's what you get. It acts on the first term, I subtract that out. Right, these two together is equal to this, right? Distribution of a derivative. This is a total derivative. A total derivative evaluated at x1 and x2. We don't make any variations there, so this doesn't contribute. Okay, so this doesn't contribute only if we don't make any variations at the boundaries. Maybe I should do two more steps. So this is equal to the x I du minus by the x and this is delta function, right? That's delta of x minus x prime. This is delta function. Cost quantity, that's also delta function. I have to evaluate this. So this integral is over now. So that's x1 to x2. Right, I finish this integral and then start the surface terms, which is evaluated at two places. The I by the u prime delta of x evaluated at x2 minus x prime and minus of evaluated at x1. Okay. These are the surface terms. Any questions here? Previous step. Oh, this is like if you have a function f d by dx of g. So this is f and that's g, right? F derivative of g, right? That's nothing but d by dx of f times g minus of df by dx times g, right? So just distribution of the differentiation, like this is equal to this plus this.
Can't we write it like since DOD, then there's a delta derivative of delta function is there, right? Second term, since there's a derivative of delta function, we can put
Immediately
DOD
put it as minus
minus
derivative,
DOD.
that's what it will come out as.
Oh.
Yeah, that's what it is, it will. So at this point, I'm sort of deriving this whole general expression. Yeah, you're right. Yeah, why not? I mean, I could have done that here, that it's easier, right? Maybe that's what I should do, that it's, you don't get confused with all this. Should I go back? Yeah, because I'm pretty much deriving the delta function proof in a sense why the derivative is
I thought
negative.
you use that method and
No. So it's usually this is how I do it. I try not to use that. Yeah. So correct. Because I have like this is the first time I'm allowing you guys to use this derivative. Otherwise, I insist the students to go through the steps. But I think this is easier. Once you reach here, you immediately say that it's the derivative minus derivative of this. That's perfectly good. That's what we will get in a minute. Okay. But that might ignore the surface term if you want. I think. Okay. Why does the surface term does not contribute? X prime is understood to be within the boundary. This whatever is your value of x prime is less than the boundary term. So these are the boundary. So x and x prime, whatever is happening has to happen within that boundary. So this is less than that. That means this is 0, that's 0. Right? That's equal to 0. That's equal to 0. So on the boundary terms, the delta function does not contribute. And if this is equal to so this is equal to di by du x prime, replace, I think this is what Manuka was pointing out, that you can immediately conclude. So let me write this down now, u of x prime. And I could have concluded that directly from here. I think what Manuka is saying is that this is a delta function. So since I know the property of the delta function, the derivative of a delta function is negative of the derivative of the whatever else is there in the integral. So that's what this will contribute to. Perfectly fine. From here, you can jump directly to this. So my point is here is that whenever you get a functional, its functional derivative is a derivative with u, then there is a derivative with, if you want, the velocity, and then there is something associated with that. When we eventually do this for the action, this will be called the Euler-Lagrange equations. Currently, this is just a functional, we are just realizing a pattern which we can always use. Okay, so this will come out. And yeah, let's stop here. So so this is a generalization of whatever we collected, our ideas, that we can always do this. Let's do a specific problems. There are two. Oh yeah, first I should give a quiz, right? Yeah, so the few class of problems that is important in this. So always a minimization, right? So you can minimize time. Minus, right? Time. And that's called Fermat's theorem. And it's a whole class of problems in the sense that given a configuration, I can tell you what is the minimum time it takes. Give me the refractive index as a function of position, and I can tell you what will be the minimum time. We have done this only for stratified medium. You can generalize this, and there is a whole class of problems you can work with. You don't have to minimize time, you can minimize position. Or why should I say position? Minimize distance, right? That's what you say. Like what's the shortest distance between 2 points on a plane? It is usually a straight line. Right, so. And those are called geodesics. Let us say on the surface of a sphere, what is the shortest distance between 2 points? If you're allowed to only go on the surface of the sphere. It's a curve, how do you define that curve? How will you, suppose you want to go from London to, let's say not London, let's say Paris, further south, right, to New York. You might see if you have flown from continent to continent, flights take a particular curve. They will try to shorten the distance because that will save fuel. And you will realize that it is not a straight line as we see it on a two-dimensional map because that's a spherical quantity. How do you decide on that curve? Which curve will, assuming wind is not playing a significant role? Wind does play a significant role in the app. They go around, usually they come around Greenland. Why Greenland?
Due to wind flow, I think from.
Assuming no wind, let's say, it's usually major component is the curvature of the Earth. It's on the surface of Earth. How do you find out which is the shortest path? So the way to do it is that have a, you know how an equator works, right? Equator is a circle that goes through the center of the sphere, right? So maybe you can try to draw. So have a sphere, let's say there are 2 points, and that's a center. So have a circle that has the center as the center of the sphere, and the center of the circle should match. So this is called a great circle. So there are many great circles. Equator is a great circle. Every circle that passes through the north and south pole will be a great circle. So you want to find one, there will be one unique great circle which will pass through the 2 points that you're interested in. Let's say this is London and that's New York. There will be one great circle that passes through it, and that will be the shortest path. On a plane, what's the shortest path? On a plane, straight line, right? That's a straight line. What if you have a surface in the shape of this room, and you're thinking of an ant, let's say, you can only walk on the on the walls. You cannot go from one corner to the other, but your goal is to go from diagonally opposite ends of the room. How will you go? What's the shortest path? Are you familiar with this idea?
If we cannot go diagonally, then we can walk diagonally.
So you're suggesting that go from here to that diagonal and then go straight up. That will be a little longer. There's a shorter path.
We cannot go through the
Huh?
wall.
Not as like, think of an ant, for example.
For
Is that
ant,
question clear?
For ant that can go.
We are the shortest distance.
You can only walk on walls. here.
Okay, only the walls, yeah, walls are the
The ceiling.
ceilings and the floor. So then what you do is that typically, think of a rectangle, you can open up a rectangle. I'll try to do this. So open up a rectangle, right? So this is a rectangle, so that's. This is the lid. The fold, does this make sense? Like think of a cardboard box, right? Like when
Oh,
it
so
comes,
you
you
fold
can,
it all in.
you can fold it out.
Thinking like this.
Does that make sense? And actually this one has, will have a, this is the roof now, right? This is the floor of this room. This is the roof. This is wall one. It's wall two, right? 1, 2, and then 3 and 4. Does that make sense? Okay. Now you realize that this is a plane, right? And we were talking about going from this corner, like this corner to, let's say, this one, right? Right, and then you realize that, oh, so straight, this is a plane now, a straight line, right? And so the idea is to go here, right? So you will walk on that, and probably ants are smart enough, and one should check. I don't know whether they're really smart enough. So, yeah, I think, yeah, I suspect. I mean, this is speculation. Is that I think assuming that ants go by smell, they depend on the chemical secretions, right? That's how they do it. So assuming that there is a smell, that will go in a straight line, so they will try to. I don't think it will work like this. I don't think they will take the shot. But I think that's
Well,
very
I think they have like explorer ants that go out, they find food, and then once they do that, explore.
Yeah, and how do they sense the distance? Probably by the shortest distance in air, I guess, by chemical.
Yeah.
Yeah, but anyway, that would be very speculative. So what thinking of the quiz? How do I? I mean, do ants follow this or not? Check it out. Do ants follow the shortest distance in a cube? Like, check it out. Okay, so that's the, okay, and on the surface of a sphere, the geodesic are great circle. And geodesics changes definitions in gravity. You say that whatever is the path of a photon. So first you say that geodesic is the path of shortest distance. So geodesic by definition is how you go from one point to the other in the shortest distance. But then photon also travels in a way that it takes the shortest amount of time. In gravity, you change this whole scenario, you define geodesic not by the shortest distance. You say the path of a photon is going to be the shortest distance. There is no other way that you can go faster from one place to the other. It is the light. So think of a black hole. The space is curved so much that light has to really go around in a non-trivial way. It is not necessarily a straight line. So that's our idea of geodesics. Third one is what if energy is minimized? So minimize energy, right? Or I should say minimize time. In a gravitational field, how about that? Or maybe even on a surface. On a surface. Like it can be generalized a lot, this terminology, and that will be called brachistochrone problems. Fourth is, what comes to my mind is minimizing area. Minimize area. For example, if I give you a liquid of water of fixed volume, a drop of water, and if I keep it in space, what's the shape it will take? Are you familiar with this? Okay, so that is what is called surface energy, which depends on the surface area. So it will try to minimize the surface area. So minimizing area for fixed, let's say for fixed, it doesn't have to be for fixed volume. there is no. The name associated, nothing, I guess. Yeah, so you just minimize the area. But here, since we are from Carbondale, that is something very,
Minimize area.
yeah, minimize the area, right? That's all. Is there a name associated with it? I don't think so.
No, I think that's just an example. If you,
What is it called?
Gabriel's horn, which kind of shows that there's infinite surface area, but there's a fixed volume. So, yeah, that does.
That would be a fractal, yeah. But, yeah, fine, close again, fine, okay. The name associated with whatever I don't know, you guys do. Okay. But we are from Carbondale, so I should explain this, or at least mention this, that if you have a film, soap film, it takes shapes. Like when we blow a soap film, you will often see when we play around, it takes the shape of a, we often call it a bubble, all right? Now, let's say that you have a fixed shape. So let's say square, cube, let's say. So the soap film can come and end on this. And now you can say, what is the shape of the film inside the cube? If you have a circle, the soap film in space will be just flat, correct? It will try to stretch out. If now I have a complicated surface, like as simple as two of them, right? If I bring in two rings, that can be drawn, I suppose. So this is two rings, and the soap film will try to stretch like this. Can you imagine that? So this is the film. So that's the soap film.
You take a rectangular cube.
No, I started with a rectangle, then I changed my mind. I can make it a two circular rings and dip both of them in a soap solution, pick it up, and there will be a film formed like this. It will be a parabolic, or what you can ask, what is the shape of this? Is that clear what I mean?
Maybe it might be a hyperbolic cosine.
Most probably that's what it will come out to be. I think this will be a catenary, but let me not presume that. We'll have to find that out. So what minimizes or maximizes the surface area? So soap film takes this shape. Now you can, the question that is addressed or was addressed 100 years back is that, can you form surfaces which are infinite in extent and they are periodic? Okay. And in all directions, in all three directions. Okay. So we are talking about a soap film that doesn't stop. It keeps extending to infinity, not just in one direction, in all directions. Okay. So you had to come up with a folding of a soap film of that form. And this was one of the answers to this was addressed by Alan Schoen. Have you heard this name? You should. He's from Carbondale. There's a faculty in Carbondale, in SIU, Carbondale. He passed away last July. He was a constant member of the physics department. He will come around, a very interesting person to talk to. He will have lots of story to tell. And he invented what is called a gyroid. So the quiz is to look up what a gyroid is. Okay. So look up what the shape of a gyroid is. Have you seen Dustin playing around with certain geometries?
Yeah.
That's based on a gyroid. So one of the classical mechanics courses, I sat in a committee where they were talking about building a gyroid sculpture in SIU. I had that figure. I kept it on the table and said, this is gyroid. And Dustin did not attend the class, he kept staring at the dirt, and that's how his whole project started. Like he then, he finds his own ways of building. You can say Jared, but now he has gone beyond Jared. He constructs triply periodic objects using helices. That's what he does. And recently he submitted a paper, so completely based on his playing around with. So those are all minimizing area. A gyroid minimizes area and it is triply periodic. It extends to infinity. So worth looking at that geometry, you should see the shape of the geometry. Right? So, okay. So those are all examples. Let's do something simple. Minimal distance on the plane. So let's say geodesic on a plane. The simplest. What's a geodesic on a plane again? Straight line, right? So, but now we want to prove that, right? So, let's call it distance. So we are saying that there are 2 points on a plane. Let's say this is x1, y1, that's x2, y2. And in general, the distance could be any random curve. Let's call that y of x. That's x. That's y. And the claim is that if it's a straight line, this distance is minimized. So the distance d would be a function of y. So it's a functional of y. And why not call it S, right? Capital S, or what should I call it? D, capital D, right? This distance, that's equal to small distances I have to add, right? That's ds. It's the integral of all the small elements that I add up. Right. So the total distance, which depends on the function y that I pick, is nothing but adding up. And since we are not specified on what I'm integrating, I have to go from x1, y1 to x2, y2. Y1 and y2 are not independent. If I know the function, then y1 and y2 are dependent on x1 and x2. ds is nothing but dx squared plus dy squared. So ds is equal to dx times 1 plus dy by dx, the whole square. So this functional derivative is nothing but, this time I can specify it is going from x1 to x2 dx 1 plus dy by dx. Y is a function of x. No, the square root. And I have to minimize this. So now we take, minimization is done by taking the functional derivative and setting it to 0. Like first take the functional derivative. We have learned how to take a functional derivative and then set it to 0, right? That's the minimization. So take the functional derivative. So that's y divided by delta of y of, let's say, x prime. That's equal to functional derivative of, this is like a u y prime here, right? So take the functional derivative, so it's x1, x2, d by dx, that's 1 by 2. The denominator, 1 plus dy by dx squared. And now I have to do the argument, so it is 2 times dy by dx. And eventually I have d by dx of delta of y of x. Clear? So soon you want to get speedier functional derivative abilities, right? I directly wrote the answer this time. I'm not explaining what. That's nothing but delta function. And as Manika said, that since the delta function, I don't have to go in the derivation. I just write minus derivative of this whole quantity, and then the derivative is gone. So the functional derivative of the total distance is equal to then minus d by dx of 2 cancels out. That is dy x divided by 1 plus. This is functional derivative. Minimization of this distance means I have to set this to 0. So
Yeah.
it should be x prime, yes. Thank you. I'm glad. Thank you. Yeah. Paying attention is very good. Thank you. That helps. Okay. Minimization means implies is equal to 0. That implies that d by dx prime, can put negative also, is by dx prime. Which means that this is a constant, right? If derivative of something is a constant, that's or 0, that means the quantity must be constant. Notice this is a differential equation now. So what typically happens is that a minimization problem gives you a differential equation. That differential equation may not be easily solvable. Sometimes they are solvable, sometimes they are not. It's like this is an action principle, it will give you Newton's law. Every Newton's law is not solvable. Simple problems are solvable, but not everything is solvable. So from this stage, not every problem may be solvable based on the initial conditions. But in this case, it is. This is a constant, and I can also write this as dy over dy of x prime. And dx prime, that's just say dy dx prime square plus dy square is equal to a constant. If I have a function like this, like here, so that was ds. That's my functional form, that's my ds. I can make a triangle out of it. That's a straight line. This is dy, that's in this case dx prime. If I say that's angle theta, dy by dx is tangent theta. And in this case, I have dy by the hypotenuse. Dy by the hypotenuse is equal to sine of theta. So I can create a function sine theta, which is an x prime dependent quantity. At every x prime, I have an angle that the curve is making with respect to the horizontal. Right. That's constant. If sine of a function is a constant, I'm saying either it is multi-valued, if theta is allowed to take only 0 to 90 degrees, then theta is a constant. If the angle is a constant, it's a straight line. A curve with a fixed angle, that's a straight line. So that's it. That implies it's a straight line. You can also do it in a different way. For example, let's say this is equal to C, that's a constant. Right. So let's go back here, dy by dx. So if I square this out, I start from here, square it, dy by dx squared over 1 plus dy by dx squared is equal to c squared. Right? Expand this out. If you open this out, so this is 1 minus c squared times dy by dx squared is equal to c squared. Right? You open this out, c squared plus c squared. Take it on the left hand side, that comes out this, which means that dy by dx is equal to c over 1 minus c squared square root. Dy by dx is equal to constant. C over this is a constant, new constant, let's call that c prime. Dy by dx equal to c prime means that's a simple differential equation. Equal to c prime, so that means y is equal to c prime x plus c double prime, right? A new constant comes in. That's the equation of a straight line. Right? So you prove that straight lines are geodesics. You could have done this like this, geometrically saying that angle is constant, however you want to do that. But the main idea is that you get the differential equation for a geodesic starting from a minimization problem. If you do general relativity, most of the problems there is it's the same idea, but now this need not be a flat surface. This is a curved surface. Think of a curved space, and you can ask what is the shortest distance, and it becomes difficult. But you can get a general equation for geodesics. A general differential equation for geodesics. They will not be solvable all the time, but for specific geometries, they are solvable. Let's do a Brachistochrone, the classic Brachistochrone problem, at least build it. Or maybe get the differential equation and the solution itself, we will see whether we have time or not. Okay, so how do you construct a Brachistochrone, or what is a statement? You have 2 points, let's say x1, y1, and there is another point x2, y2. Okay. And that is gravitational field acting downwards. So this is uniform gravity. It's not 1 over r square. One can generalize this problem to say that what if it was 1 over r square, but we are saying uniform gravity, we are on the surface of Earth, and have any surface of your interest and roll a ball perfectly on it. It shouldn't slip. It shouldn't slip or slide. Okay. It should, by rolling perfectly means the wheel should touch at every point. Like when we are driving on the interstate, most of the time we are perfectly rolling. Like it is not slipping. Or another statement that I can say this very clearly is if I have a radius r, this is rotating with an angular velocity omega, and the speed here is v. V of the velocity of the center of the sphere is v. How far this goes in the horizontal distance x, and how far it goes in the angular distance theta is related by theta times r, right? That's an arc length. arc length of a circle is theta times r. Velocity, take the derivative, dx by dt is equal to omega times r d theta. By dt times r. So v is equal to omega r. It is possible that x is less than theta r. Right. That's what happens in snow. This is called slip. And example is snow. If you experienced a wheel rotating in snow, it doesn't move forward. It spins a lot, but it does not move forward. Think of an extreme scenario. I think Ryan is smiling, probably.
I was just thinking of be kind of like ice. Ice should be really different stuff.
Ice is different. Ice will be sliding. We want to keep ice. This is like mush. This real snow where you get stuck, like you or mud. I mean, if you're if you're from tropical countries, think of mud. Like there is so much of mud that you cannot. I mean, you can do everything, you won't move forward. You're just stuck there. Your wheel will keep rolling. Like a mud is for tropical countries. If you're from cold countries, then you think of snow. Okay, clear? Now, this is the extreme limit, right? Snow. And now if x is very much greater than theta r, that means it is moving forward, but it is not spinning. Right? That's what happens on ice. So the wheel will just slide, it is not going to spin. Right? So that's slide, like extreme version. Right? So it's slide. And this is ice, perfect ice. Right? But we don't want either of them. We want perfect rolling. X equal to theta r is perfect rolling. So whatever is moving from here to there, it has to perfectly roll. During perfect, why I insist on this is that during perfect rolling, we are not losing any energy in friction. Like we always say that during friction, we lose energy, but as far as your wheel is perfectly rolling, you don't lose any energy. Why is that?
That energy is being transferred from rotation to translation.
That's correct. That is correct. The friction helps. The way to say it is that
Propel the vehicle.
friction helps rolling. And frictional force resists translational motion. Friction times the distance traveled is the work done by the force, but they cancel each other only in perfect rolling. They exactly cancel each other, and friction is not doing any work in a during perfect rolling. It does not do any work. So you don't have to worry about work done by friction. It is only gravity then. If friction is gone, then I have only gravity worrying about. So let's talk about the kinetic energy plus potential energy. In this case, mg times, let's say, y, right? Mg times y is equal to a constant. In general, since there is another force, friction, I have to take care of the work done by friction also. But in perfect rolling, I don't have to worry about that. So it's only gravity and velocity. What is that constant? Let me say initially that it is at rest. So rest. And if it is at rest, I can calculate this constant by the velocity, kinetic energy 0 there plus mg y1, right? Potential energy there is y1. That helps me calculate this. So m cancels out. So v is ds by dt, right? ds by dt. Remember, this curve is not necessarily x or y. That's ds. Small element ds by dt. So let me two steps. So half m ds by dt square is equal to mg y1 minus y. So dt or m cancels out. So ds over 2g y1 minus y is equal to dt and then square root. This is the time. This is the time it takes to travel this distance.
Use the camera.
Oh, I didn't use the camera at all. Okay. Should have said that. That's a long time, I guess. You guys should tell me. Well, you guys. Okay, sorry about that. Thank you, Naila. Okay. So. The time taken to travel this tiny distance is the tiny distance ds divided by y minus y1. Okay, where y is the coordinate of this point, x comma y, x2 y2, x1 y1, and that's what it is. So the total time will be, just integrate, right? So total time will be, add up all the quantities starting from x1 y1 to x2 y2. That's the goal. We want to minimize this. Our question we are asking is that for what y is, for which curve y is this minimized? Is this time minimized? Or examples you can have is this a straight line? Is this a circle? Is this going all the way down and coming back? Usually the argument is that if you go further down, you go faster and faster, you gain a lot of speed. By gaining speed, basically what you're doing is that you're reducing time. So you would think that going deeper is beneficial. Like go deep, but then you're going way far. So somewhere there is an economization, or if you don't want to go too deep, you don't want to not go deep at all. So somewhere there is a optimal path that is there, and that's what we are looking for, and that is got by minimizing this quantity, right? So it will be x1 to x2. If you want dx, let's say x1 y1 still, and x2 y2, and minimizing ds over 2g y1 minus y. Okay. ds, the same idea as earlier, can be written as x1 to x2 dx, and you have 1 plus dy by dx square root, that's ds, and then 2g y1 minus y. And we want to minimize this. There are two places where y shows up. There are two places where y shows up, so there will be two terms in this. But I won't be able to finish this. I have only 5 minutes because I have to show that this is a cycloid. So we'll come back on this. So here's a quiz. We can do some homework. So quiz related to this. One is find dt over dyx prime. This is dependent on y. So find this, and the second is find the equations of a cycloid. What's a cycloid? Any?
Rotating and going forward.
Rotating and going forward. So the best way to see it is that have a bicycle wheel and have a small LED light connected on the tip of the rim. Put it in the dark, right? So that you don't really see the rim. And now make it roll, like make it perfectly roll. And what will happen is that you only see this light. You will see that this goes like this and then goes like this. That curve is called a cyclone. And if you invert this curve, that's what this brachistochrone will be. It will turn out that between connect 2 points along this on this cycloid, and that will be your brachistochrone curve. But that will take a few minutes, so we will do that next time and slowly proceed forward. And I'll also try to do the great circle problem, maybe that can be done in the class. I'll decide which problem to put on the homework and which one to do it here. And we'll go from there. Thank you. Any questions in general?